If you have any questions, please let me know. Good morning. Last week we were focusing on color blindness. Let's continue from that point. Thinking of color, significant portion of people in the population are colorblind. It is 8% of the men and 1% of the women. Therefore, when we are designing interfaces, the reliance on the color should be limited. So color should be only used for additional information, not for a crucial information. When the color is used, usually, as you see at the top, it must be given with additional information together, such as in the figure, we will see the stop sign in addition to the word. So only red symbol is not sufficient. So if you are colorblind, you will see the word. If you are not colorblind, you will see the color plus the word, so it will be stronger, and that will be sufficient. So do not rely only on colors. That is the idea here. This was the test for those of you who were not here last week. That's one of the examples of color blindness test. I'm sure we have colorblind people among us. And now we start with the contrast concept.
Hocam, what was the right picture writing? I couldn't read it.
Yeah, right picture does not have anything.
Okay.
So you shouldn't have anything there if you are not colorblind. If you are colorblind, you will see something. Now we think about contrast concept. Giving information only with the color difference is not sufficient. So you have to differentiate not only with the color, but also with the intensity. So color is not sufficient. Therefore, we have multiple definitions for that property. One is the luminance. Luminance is actually related to intensity. So the amount of light emitted by the object or from the screen depends on the amount of light falling on the object and its reflective properties. If it's a real-life object, obviously it has to be illuminated unless it's a light source. Therefore, it depends on the color and tone of the shade of the object. Contrast is a connected function of the luminance. Relative values of the luminance of an object and the luminance of the background. So background versus foreground in terms of intensity, light intensity, in terms of luminance, is called as contrast. So contrast is one of the fundamental things in the proper screen design. And here is an example. We have luminance contrast and color contrast. Obviously, color contrast is interesting additional properties that we will see. When you have high intensity contrast, it will be more effective. When you have low intensity contrast, so the reading will be, on the reading and comprehension, will be more difficult. Using only color contrast is not suggested unless there is a well-known reason. Sometimes there are reasons. So if there is a reason being, for example, here as yellow, then it could be, but having red here is not preferred. So this must be black or blackish or brown. So pure red is not good for these signature purposes for displays. Furthermore, let's make things more complicated. Here, intensity contrast are equal, but color contrast only. So color only is not actually sufficient, and it's very tiring for your eyes and difficult to comprehend. So when we only rely on color for representing the shapes, we will have problems. So these edges won't be understandable. So with the intensity, it will be much better, or together. If you combine them together, that's okay. But only on color difference, is very dangerous. So if you make this kind of interfaces and expect user to use it, at the end, people will fail, and you will blame people, indicating that you made the difference, but actually you made the difference so bad that people couldn't use it. And the use of color in the interfaces are various. It could be for labeling, for example, red versus black. Usually, red is more important. Some more important things are labeled with the red color, or something related with the health of the system. Such as red is dangerous, bad, whereas green is associated with good, good behavior and healthy behavior. The selection of low and high depends what you are trying to convey as a message. For example, having something high could be good in certain applications, such as fuel level. So if you are thinking about fuel, high fuel is good. So here you have, for high values, you have green. But when you are focusing on something that needs to be low, for the normal case, then you do the opposite. So you put green on the left, green on the left, and red to the right. So if needle goes from green to red, that means like temperature is increasing, the reactor temperature is increasing, or pressure is increasing. So it is becoming dangerous. So it is reversed. How about blue? There is blue, green, red. In this case, you are expected to stay in the middle. So lower values are not good, higher values are not good either. So depending on the application, you need to choose the color scale and orientation of the colors to label what is high, what is low, what is good, what is bad. And you should think, you should spend some time thinking on what to implement. Otherwise, people will understand incorrectly. For example, sometimes you have yellow here. As a designer, you may be pushing the idea that yellow is a good thing, but some user will believe that they need to stay in green area rather than yellow, because yellow is something like little bit dangerous. Okay, but sometimes some danger is there. Therefore, depending on the application, depending on the variable that you are controlling, you need to rearrange the colors. Sometimes it is only for decoration or for technical purposes. That's green because that's a design choice, but some colors can be different a little bit to indicate those keys are more important than others, like turn on and off. Some certain colors are associated with certain functions, such as in phones. The red button is usually associated with the hang up. We are using Teams right now, and in the Teams we have the leave button, and leave button is red, so it is labeled as in connection with hang up function of the mobile phones of the early days. These are also colors that has slightly different functions than others. So when you have slightly different function, an important function, or something related to an external object, then having a different color, labeling it with different color is the choice. A famous Stroop effect. This could be an exam type question. I sometimes ask this in the exams, not always. When you have conflicting information regarding the color and the information contained with the label given with that color, if they conflict, you are confused. That confusion and that interference, that is called as interference, confusion. That confusion, and that also results in success rate and reaction time changes. So reaction time becomes longer, so you spend more time to understand that those are meaning something different. And if there is a question related, and the success rate of the question is reduced, such as my favorite of these three colors is forest green, fern green, forest green, chill blue. So you are thinking, in terms of color, but the label colors are different and conflicting. Therefore, you will have difficulty. So you should not cause. Obviously, this is exaggerated, but slight Stroop effect can happen anytime. So you should be careful in making those. For example, when you have thank you, teşekkür ederiz, in red, in a message, and also with an exclamation mark in a dialogue, user may understand that there is an error. They may think that there is an error because it is in red. So red meaning conflicts with the content of the message. Or aradığınız sayfa bulundu. Aşağıda sıralanmıştır. In red. So this says the page you have searched has been found and the results are below. But since they are written in red and bold, you will believe that even if there are results at the bottom, you will believe that something is wrong there because red is associated with errors. Therefore, it has to be green. The opposite also is true. Ramazan says Asian countries red means positive. So yeah, for the Chinese user interfaces, text written with red is not perceived as bad as Western societies. But over the years coming, that might change because global culture is unifying. So although there will be some positive meaning of red in East, I think it will change on one side. It could be our side or it could be their side because we will be interacting more and more. The color spaces will be studied in computer graphics course, and this year Gökhan Hoca is giving that course, and you will be going through those. But generally, we have different color spaces to represent color. The reason of having red, green, blue. The reason of having red, green, blue was actually explained in earlier class, and it's related with the cells in our eyes. So depending on the frequencies, when we add those different components with the proper amounts, we can generate the illusion of. It's not illusion, but it's sensation, perception, not sensation. Sensation of colors, of thousands of different colors by changing the amount of red, green, and blue. If you are generating the light, such as you are using the LCD monitor or TV or light bulbs or LEDs, whatever, or OLED, organic LED LED displays, then RGB model should be used because you are generating light. However, if you are into printing, if you are absorbing light, that model is not easy to use. Then, because when you have an object, if this object is red, that means light comes in, light comes out. This is your eye. Okay. And you say it is red. Fortunately, my pen is also red. You are seeing it in correct color with the example. So why do we see it in red if it's an object, not you are seeing it from screen, so it is in RGB now. Now you are seeing in RGB. That color is generated in RGB. But if it is printed on the paper, then there is something related with the absorption. Some color, some frequencies will be absorbed. Some frequencies will be absorbed, meaning that some will be reflected. The reflected ones will go our eye, and our eye will perceive it as red. So if I put a paint here, that paint should absorb certain color, and that is actually cyan. If I paint if I absorb cyan, meaning that meaning that actually no. If I absorb blue and green, if I absorb blue and green, then I will see the color as red. So in order to do that, you need to paint it with yellow and magenta. When you paint it with magenta and yellow together, that means you are absorbing blue, and green. When you absorb blue and green, what you didn't absorb is red, so the object will appear as red. Okay. So that CMYK model is based on absorption. Which frequencies you absorb. You paint with one ink, then one frequency type is absorbed. You paint it again with another ink. You paint some other frequencies. So then that makes the combination of multiple frequencies for color painting. CIE is an acronym for Center of International Éclairage in French. This standard is made in 1934. So they standardized the colors. And obviously, this is based on the human perception, test human perception. These are the colors in rainbow, and the rest is the color that we can see. You have x-axis, y-axis, and you have the z-axis. Z is actually 1 minus x minus y. Therefore, x plus y plus z is equal to 1, and that is the CIE model. In the CIE model, it is something very similar, although there are coefficients, something similar to RGB model, because in our eyes, remember from the last time, the values of the sensors, the sensitivity of red, green, blue sensors are not the same. So they are not unified measurement devices, red, green, blue cells in our eyes. Therefore, rather than equally spaced, well-balanced X, Y, Z, we have a color gamut. That's what we said. So it is CIE chromaticity diagram. Gamut is here. Each display has a gamut in the CIE diagram. In the CIE diagram, X is related to, somewhat related to red, the reddish perception. Y is related to green perception, and subtraction of X and Y from 1 is actually Z is related to blue perception. That could be represented in 3 dimensions as well. You will see that in computer graphics class. For the user interface design, contrasting colors, using color together has significance. Strong contrasts can be achieved by using primary colors in red, yellow, and blue. One thing is, in the CIE chromaticity diagram, there are complementary colors. For example, color from this part and this part are called as complementary because there is a white in the middle. So if you keep things if you keep white in the middle and pick colors from the rainbow edges, then this is the rainbow edge at the top here, and another one is at this one is bottom rainbow edge and the top rainbow edge, or this one and this one. So one color from here, another color from the bottom. So white is at the middle. Therefore, that is called as complementary color. Okay. Here. So 2 complementary colors, another complementary colors, etc. And if you combine complementary colors equal amount, if you give complementary colors together from distant, they will be perceived as white. So that the linear combination of this color and this color will make a white. When you have 3 different primaries and you give equal amount of these 3 let me erase it. One from here, another from here, another from here. So if you give proper amount equally, relatively equally, depending on the shape of the triangle, then you will get white. Again, this is not for painting. This is for illumination, for light generation, generative model. HSV and YUV are used for different purposes. HSV is used for artist and painting with the colors. So representation of colors is easier. This is hue, saturation, and value. So hue is actually indicating color. Saturation is how black is it, how pure is it, and value is what is the brightness. So it is easier to find the color that you are looking for as you are playing with the colors and making design, graphic design. YUV is more into broadcasting technology. It is better for analog type displays, and that's how it emerged. So primary color contrast. So this is Galatasaray, this is Fenerbahçe, and this is Trabzonspor. Galatasaray, Fenerbahçe, and Trabzonspor are actually using a primary color contrast. When you combine these two, you'll get usually whitish results. So it is from here to here, etc. This is Fenerbahçe. Sarı kırmızı. Usually this is, yeah, that is not proper, but it is considered as primary. And red blue is here. Fenerbahçe is, no, Galatasaray is not complying it very much, so it has to be pinkish to yellow for proper contrast. Second, for the same color, you may use different tones of it. That is what we call brightness or intensity contrast. We have seen that. Brightness contrast can be used for the same color or same gray with different values of illumination. You may have use for that in the interface. Hot, cold, warm, cold associations, contrasts can be used. These colors are associated with warm, and the bottom colors are associated with cold. So for designs like increase, decrease kind of displays, those can be used. Usually warmness is related to the warm spectrum of the visible light. So from which side is actually matters. Near, far, good, bad, hot, cold, more or less, those kind of. Sometimes more is good. So if more is good, it should be associated with green. But sometimes more is bad. If more is bad, then it should be associated with red, or if it is not as bad, it should be associated with yellowish or orange color, so that it is getting bad, not as bad, but it is kind of bad. This is what we said, complementary contrast, yeah, rather than primary contrast. When you combine them, you get a complementary contrast. As I said, Fenerbahçe is complementary contrast, good. And what is this football team? There was one. I forgot. Anybody remember which teams are this? So those use complementary contrast. When you combine them, you get white. Quality contrast. is done by, and the HSV model, hue saturation value, hue saturation and value. With the value, you have brightness contrast. That is what value, that is when value changes. Hue contrast means color contrast, but saturation changes are associated with the same hue. Hue means color. With the same hue, different saturation values gives you different quality. So this is called as quality contrast. You can differentiate things on screen or interfaces or on objects using the color quality, not the color difference. That's also possible. And quantity, color quantity is an interesting term. Some colors have more weight than others. As another example. For example, when you are using this violet and green, if you use equal amounts, this becomes dominant in the design. Therefore, you will use less of the dominant color. Color dominances are very interesting. For example, yellow 9, orange 8, red 6, violet 3, blue 4, green 6. So if you want to use red and violet, you have to use 6.3, 6 to 3 ratio. That means red surface has to be twice as big as to be perceived equally. That's an interesting issue. Okay. Oops. There are, we have other examples from the book. This is a good example of color contrast. So Fenerbahçe. Warm, cold contrast is similar intensity but different colors. So this is warm, this is cold, and then this is light and this is dark. Different values of contrast. Sometimes opposite color is created by our eyes, so that's what we call simultaneous contrast. The effect of our vision system is used to create contrast. We see some brownish effect in the middle, although it is gray. We see some colorization. We see some artificial colorization by our senses. That is called a simultaneous contrast. So it is not found in many places. Some books talk about this. Complementary contrast is using color wheel, meaning that color CIE diagram. That's related to CIE diagram. A new idea is split complementary. And again, this is color wheel. Instead of using the opposite, and you need 3 colors, one from one side, across, split. So these two. Then we can generate these combinations. These combinations are good tree combinations. For perceivability. For yellow, the other two. For example, when you have red, you have this and this, etc. You have these two as well. If you have any questions, please write so that I can read it. I have the chat box open in my primary screen. How and why are we using colors? And for labeling, the colors must be distinct and distinguishable. If you are labeling something, associating something with the color, then these are the recommended. Yes, Ramazan. These are general colors that people can name, and if you are going to not decorate or not use for buttons and differentiating elements in the screen, but using labels to indicate something, then use well-known distinct colors such as these. Last time I have explained this little bit, but here comes again. Blue text on red background or red text on the blue background is hard to read, and that is what we call chromatic aberration. Chromatic aberration is the following thing. Since we have a prism, actually it's a kind of prism. Lenses are prisms actually. So this is the lens, right? And when you focus on this part, it behaves like a prism. So that's how it refracts the light. So it's if it's a continuous round prism, we call it as lens, a glass lens or plastic lenses or whatever, but lens. So not all frequencies are bent at the same amount. Our eyes also suffer from this, and so focusing is problem. So when you are sending different frequencies to the eye in different colors, they don't exactly focus on the retina. So your eyes will have trouble keeping that up. Therefore, pure red and pure blue are, for example, the most, because they are very significant. Here, blue is early, red is late. So you are trying to focus on green. So anything, if everything is blue, then your eye will adapt. But when you are sending different wavelengths, the eye will focus on the most dominant one. But as the color changes, you have to reposition your lens. So your lens constantly readjusts, and your perceptual system works much harder, and that becomes tiring, and it also increases your reaction time, probably. I have no strong answer to that, but probably it will increase your reaction time. I haven't searched for it. Another interesting and actually very interesting topic is red light does not prevent eye to adapt to the dark. Because rods in the eye do not respond to red. They are sensitive to black and white, and they are less sensitive to red frequencies. They are more sensitive to blue and green frequencies. Therefore, if you don't want to disturb red light because they are associated with night vision and darkness, but still want to give some light, use red, because when you use red light, rods are not stimulated. So at the same time, if anything comes from distant in the dark part of the road here, for example, in the car, or if you are in a military vehicle, you have some displays, but those displays are emitting light, but you have to see outside. Therefore, you have to see from the dark. Therefore, using red instrument panel makes your life easier, and your vision is improved. Therefore, in the car dashboard designs and military vehicle designs, usually low light and red light possible increases the performance. Or when you have a device that will emit a light during the dark, such as in the bedroom, a charging indicator, a charging lamp in the bedroom, or some television standby lamps. So red is actually the most tolerated ones in the dark by the eye. So it does not interfere much with the other dark vision. That's important. Furthermore, if you want to see more in the car, turning on more lamps will not help much, because or putting blue light does not help much, because that those powerful headlamps increases the brightness of the oncoming road only. If the road is very shiny, if the road in front of you is very shiny, this is your eye, lens becomes smaller. When the lens becomes smaller, distant objects, which are usually dimmer, are less visible. In addition to this color issue. Therefore, instead of having too much light in the cars, for example, you have headlights and you have fog lights. When you turn on fog lights, these are headlights. When you turn on fog lights, the road becomes more illuminated. Road becomes more illuminated for rain and fog. But when you turn on when you turn them on for regular use, your eyes, iris becomes smaller because the road is more shiny, so that you cannot see the distant individuals and very distant objects. Although you are seeing more shiny road, illuminated road, the vision is negatively impacted. So here is what we are doing for the reading. When we are focusing on reading, our eyes move. Our eyes move, but actually our eyes doesn't move continuously like a scanner. It does not move continuously as a scanner. It move, stop, move, stop, move, stop, move, stop, move, stop, and so on. So there are some fast movements and then stops one after another. Usually fixations take about 100 milliseconds to 200 milliseconds. Depends on person, attention, age, if the person has some medication, it all changes. During that 100 millisecond, your brain captures the image and moves to the second part. Next fixation, next fixation, next fixation. It's an automated process. So a good reading is sometimes desired, sometimes not desired. A reading is affected by the following parameters: angle, illumination, contrast, color contrast, line length, upper or lower case, or familiarity. If you understand the language, then you can read faster. The fixations will be shorter if you know the language. Actually, I was involved in a project dealing with children with reading disability, dyslexia, when I was doing my PhD, and we found that these fixations are a little bit longer for children with reading disability. And furthermore, I realized that it also changes when you are reading a foreign language. If you are reading a foreign language text, English as a foreign language, like we are doing now, our brains work differently than native English speakers. Therefore, we were able to understand by eye tracking that whether the person is a native speaker or a foreign-born person speaking English with secondary language as English as a secondary language, like us. And there was a reading out loud experiment that I was doing, and there was a book. Person was reading the book, okay, and he or she was speaking. As he reads. And in the brain, it must be processed and it must be spoken out. So there was a time difference between the fixation and the speaking out. For the foreign people, and English as a foreign language people, this time is longer. For the native speakers, that time is shorter. Probably the processing in the brain is taking more and following different paths so that it takes much time. And with the children with reading problems, that time was variable significantly. That wasn't constant. That time was significantly variable when you have a reading problem, reading issue from the childhood. That was an interesting study, and if I will have students that are interested in eye tracking, maybe I will focus on that topic again. So studies are done in reading by a lot of people, and they found out that optimal line length is for fast reading and good comprehension is between 6 centimeters and 13 centimeters wide. So between 6 centimeters and 13 centimeters is the good reading. Anything longer than that from the reading distance, anything longer than that will be read more difficult and will be read slower. Second thing is text printed in capitals was read 14% slower than lowercase text. So if you want to be read fast, please write lowercase, and that's an issue in the social media, you know, and typing in the uppercase means shouting, so lowercase is more like regular text. Uppercase is effective, therefore, for emphasizing words such as labels, such as signs and orders, etc. So if the text must be given as an isolated manner, then uppercase is then good. Ben Schneiderman has done an experiment, and his student was also Turkish, and the experiment resulted in that reading from computer screen was 15 to 30% slower than reading from the book, and that was in 1998. It is still regarded as a reference, but more studies are necessary to compare between tablets and regular screens, etc., laptops, and type of the screens and phones. So reading a book, for example, from the phone or from the regular book makes some difference, but the problem is how much difference we have. That should be measured. Do you want to give a break? Okay, let's give a break and come back in 10:44. Okay. Okay, I'm back. So, this time, herkes geldi değil mi? Uyanın. This time, we will be reviewing the famous laws of vision called as Gestalt laws. Interestingly, the word Gestalt doesn't mean that the person who found the rules. Rather, it's a German word named for pattern. There are 7 rules, basic rules. There are also associated issues with these Gestalt laws, but the famous ones are 7, and those rules describe and make the mechanism about how we perceive information on screen and how we perceive information in our surrounding. These are proximity, similarity, continuity, symmetry, closure, relative sizes, figure, and ground. So these are Gestalt laws. So I'm going to give examples on each of them right now. This is what proximity is. What do we see here is actually a bunch of dots. Bunch of dots. These dots are perceived as a group because some of them are closer than others to each other. And the ones that are closer are seen as lines, although you don't have line. Do we have lines here? No, dots. But we perceive lines because of the proximity association. So our brain tries to complete things, tries to connect things, so that even the dots are perceived as lines because they are closer to each other. So when you are placing things on screen and when you are making a design, things that are close to each other are usually perceived as they are related. For example, the one on the right, they are perceived as 2 different groups, 2 different sections, because there is a proximity issue. If I cover them with a certain red line, then we start to perceive them as one set because it is encircled with a surrounding. So if not, we perceive as them as 2 different objects. This is what proximity tells us. Proximity can be played in different ways. One different example is density-based proximity. So there are coarse ones and there are dense ones. If you want to group these together, your brain perceives the following: the right part as 1 and the left part as a second group. So your brain comprehends this as two different groups, although there is no mathematical or physical direct relation. Although if you make data mining and the clustering algorithms, apply clustering algorithms, and you can find this clustering, but as an interface, as a real world issue, your brain automatically perceive it as two different groups. Second thing is the type. Similar things are grouped. Similar elements needs to be grouped. In addition to proximity, similar things are brothers. Therefore, when you have crosses and circles arranged equally spaced, but your brain tends to construct lines. Out of it. So similarity also affects brain to make them make different things related. So brain makes different things related because of their similarity. And the brain tries to form bigger abstract entities. And here in this example, that entity is line. In other examples, the entity could be different shape, different object. Sometimes an image can be conveyed. Distantly related to the similarity, our brain tries to continuate, tries to have continuous lines rather than discrete lines. Abrupt changes are not liked, because in the nature, abrupt change is usually associated with broken things and things that are not good. In the nature, many things are continuous. So our brain tries to understand the environment as if the lines we see are continuous. Therefore, when we are giving this figure to the user, and user will perceive it as this one, but not the one on the right, although the figure can be something like on the right, but our brain never understands it, never thinks that it is the figure C, but our brain tries to accept the idea that B is actually the relation between two different lines, two different pieces of dark lines in the figure A. So that's how we understand it, continuation. Abrupt changes are less likely in our perceiving, in perception. When we connect things with the continuity, we make them related. Distant objects, normally you have so if there is an on-off, usually these are related because they are closer. But if you connect them with visible lines, right, or if you connect them with boxes, with background boxes, with different colors maybe, then we try to see them related. For example, this is an on-off switch, on-off. One of them will be on, one of them will be off if there are two buttons. But if this one doesn't exist, then you will try to associate up and down with the arrow, up and down, because they are closer. Having both is better. So connection plus boundaries, or some relation with the color and the lines, surroundings, types, and you make them, we associate them. And if our task is to associate them for the good interface, such as up, down, on, off, positive, negative, so same variable but two different controls, then this is the way to go. In here, there is a conflicting, something like a Stroop effect. They are connected, but also colors are connected differently. Even then, also the shape, even then the connection is stronger. So having them connected, like with the lines or with the boundaries or together, is more stronger than shape or color. So when you have them, they are associated as commanding to the same variable in the interface. Our brains like symmetrical things. Unsymmetrical things tend to get memorized more difficultly. So the figures on the right, two figures on the right, is easier to memorize, whereas this one is less easy to memorize. Human brain tries to group symmetrical figures and try to simplify it so that it can store it somewhere deep in our neurons. And continuity has the closure property as well. Is this a curve or a circle? The question is this a curve or a circle? The answer is actually, it is, the technical answer is that's a curve. But perceptive answer is it's a circle, because our brain tends to close the gap. Yeah. The last one is relative sizes and figure and ground. Relative size means if we have something smaller and something bigger together like this, smaller components are perceived as moving and components, where bigger parts are seen as background. So when we have something like this, usually we perceive it as we have black fan rather than white fan on the black background, because black regions are smaller, we see black fan. So designing the screen, designing the interface, when you have things that are so big and other things are small, big things tend to get associated with the background. So it should be, the sizes should be relatively small enough to be perceived as an active object. And what do you see here? A classical example. Do we see two people here, or do we see the vase? And actually, human brain tends to pick up forms based on the previous experiences. If the person is blah 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 blah, then some people form it two people, and the others are actually perceiving the vase depending on the psychological issues. But general tendency is having smaller things having smaller things are associated with the objects. The other bigger things may have some object definitions like this, but actually it's not realistic because you cannot have, oops, sorry. In this way, you can perceive the person, but if you don't have realistic sizes, then usually the vase is perceived. Okay, that's what figure and ground is. Next is the optical alignment. That's an interesting design in the font and screen objects and computer drawings. And when designing good fonts, good readable fonts, people are having hard time because, for example, the bottom part of the, where is it? Bottom part of the, what happened to my pen? Okay. Bottom part of the O is slightly lower than N boundary. So there is a slight region that is allowed for some certain characters to pass. So why do we have that? The reason is that since the certain parts, most parts of the letter O is above the line, in order for a person to feel that the letter O is on the line, it has to go further down. Even if it goes to further down, then we perceive it as if they are on the same line. So it is not what matters that they are on the same line in reality. It is how you perceive it. If you perceive them to be on the same line, they are on the same line. If you don't perceive them on the same line, but they are on the same line, they are not on the same line, because it doesn't matter whether in reality where they are. It matters what you see.
Something like this happened back when Google was designing their new logo, like
Yes,
2016,
exactly.
2015.
All looked smaller.
Yeah, all looked smaller, and the colors were not aligned perfectly, because when they tried to align it perfectly, people wouldn't like it because they didn't look similar enough. They didn't look perfect enough,
Yeah, exactly.
even if they are perfect.
Exactly. And the next example shows the principle. That's what we call optical scaling. In the first figure, the sizes are equal, but the perception of these three figures is that this one looks smaller because the area is total area is perceived rather than the upper and lower edges. So your eyes don't measure the height, your eyes measure the weight of the object. So in order for them to appear in the same size, that's also similar for the buttons, physical buttons. These ones should be made a little bit taller, so that it will be perceived in the similar size. That is related to, again, with the font design. For example, font I and font M and G. What do we have? N, Z, or B, or whatever. So these are different fonts, and each of them has various and different ways of drawing and the visual weight of each letter can be different. So font designers take that into account, and sometimes they add additional parts. For example, instead of writing T, they have such as the font times, they have additional parts for the standard definition. So why do we have this? Because when you have that weight there, human eye and brain perceives it better. So that font will be read better. Therefore, as a general purpose, we have serif fonts and sans serif fonts. Sans serif fonts are Arial, Verdana, etc. And this is Times, Calibri, etc. So it is easier to read these serif fonts rather than sans serif fonts. Sans serif means not serif, because these edges have no balancing property as an additional balancing property. We don't focus on geometric shape directly. We focus on certain well-known parts, differentiating parts. So, for example, serif font does this for the letter O, so it is perceived better. And the area between, this is another design issue for the font. Area between two letters may not be the same. If you use same distances, reading becomes difficult. You have to have variable separation. For example, in between, you have maximum separation. In between this, you have less separation because optical alignment requires you to have less separation. So generally, the area here and here are effective to determine the distance between two letters. With a careful design, good fonts, good font families, and word processors can be implemented, and the output will be a lot readable.
When the space is even in all letters, we call this monospace,
Yeah.
I think.
Yes.
Fourier, yes. I think they were using back in the typewriting days.
Yeah, exactly. In the old days, in the typewriters, you have to have equal space, but in the printing, you have remember lead letters made by printing office, and those letters have variable space because they are made up of small pieces, and although the vertical length of the big piece back plate is the same, the front containing the letter was designed by the printing master or somebody who is responsible for making those letters in the printing office. And what they do is they put those LEDs one after another by hand to make the book for print, to make the page. So that is typeset. That is called as typesetting, I think. and that has variable sizes and all those. But for the typewriter, that wasn't possible, so equally spaced letters were the norm. So if you have books from early centuries, like 18th centuries or 18th centuries or 19th centuries, you have variable size fonts for the letters, but for the typewriters, they are fixed size. Okay, so much for the vision. We have few things for hearing and touch, although we can talk about more. We have certain interval for the hearing, but actually it is up to, for most people, it is up to 12,000. And the hearing ability is diminishing at higher frequencies. And we have active filtering effect, cocktail party effect for the ears. For example, we can eavesdrop two people talking in the cocktail party and still understand. And that's called as active filtering, and that's available, that's becoming available in recent desk microphones for the meetings. When you have multiple microphones, you can you can orient yourself so that you can only pick up for sound coming from one direction. If the person is talking from one direction, you can suppress the other sound coming from other directions. That is done by having multiple microphones in the human head. So you have this air, this like an tape. So there is a time, if the sound is coming from here, there is a time difference. There is a time difference for the sound to come to each of your ear, and your brain perception system processes it so that it can ignore the sound coming from A, but it can focus on sound coming from B. That happens, so that's an interesting property. So active filtering is available with the hearing. And we use sound for status information, error information, using beeps and sounds. So it's interesting. It's an additional to interfaces and cannot be the only output, again, because the person might be deaf, or sound might be turned off, or the environment could be very noisy. So in those cases, we cannot use sound. Therefore, sound should be additional as a supplementary interface. It reduces the cognitive load on the visual channel. That's interesting. You see something, plus there is a sound. So sound might be seen as redundant, but actually it is not. So sometimes it reduces the cognitive load. Even if you see it, supplying it with the sound feedback together makes you more comfortable, and that reduces the load. Sound interfaces could be annoying if improperly used. So unwanted beeps, chunks, etc., such as this. There is a project meeting for the Didem Hoca at 11:30. For those of you who are taking, who may take project from Didem Hoca, should go to her meeting in 15 minutes. So musical notes must be considered when designing sound for the output, such as there are positive sound, positive 3 sounds, and negative trio sounds, harmonical good sounds and bad sounds. Those sound combinations should be carefully designed. And passing from the gate with the card reader. Okay, you are going to pass. You have your card read and there is a beep sound. The beep sound sometimes is a good sound, good beep sound, and bad beep sound. If the sound is a bad beep sound or a random beep sound, the person may not understand whether the card is read or not, read positive or not. So if it's a metro station, if it's a cafeteria and the company entrance or campus entrance, there are sounds, or bus ticketing system. If the sound is positive, you automatically realize that the transaction is, or the control is successful. If the sound is a bad sound, it's a musically bad sound, then transaction is bad. So designers should take that into account to convey information in addition to the display information, because only when you have only display information, people has to look for the display all the time. But if it is supported with the sound, then you don't have to. And there are additional environmental effects when you have outdoors in a market, etc. So audibility changes. So you have to have different volumes. So environment noise must be checked, and the sound from the interface, such as if it's a telephone, for example, the telephone should check the ambient noise in the surrounding. So if it's a silent room, so the sound interface, sound feedback should be lowered. But if it's an outdoor environment, then it should be increased. The volume should be increased. Okay, then as similar to vision, the perception is logarithmic, meaning that in the silent environment, differences can be measured much better. Same amount of difference can be perceived much better than with the noisy environment, with the higher values. Therefore, decibel differences, which is logarithmic, is used. So when you are increasing decibels one by one, that means perception is actually similar, has similar linear changes if the change is logarithmic. If the change is linear, then for the higher ends, you don't see the difference because it doesn't make much difference. It is all loud. Therefore, it has to change much more for the louder values. That's what we call logarithmic change. The last sense that we utilize for the user interfaces mostly is the touch. Touch is interesting. Below you see the device for the blind people. Blind people hold something at the bottom that is rotating. That knob is rotating, and the speed of rotation and vibration, etc., gives certain information. So that is how you understand the condition about the street lights. So you can check the status of the street lights by touching, not by hearing that şimdi karşıya geçebilirsiniz, şimdi karşıya geçebilirsiniz, or beep 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 beep, beep etc. So that will make other people crazy. Rather, some slight feedback, some slight voice feedback, and pulling the person into a haptic interface and having the condition checked is much different design. Obviously, I am not suggesting that this should be a design for all the streets, but for certain places that can have certain impact. Touch interfaces are not only for people who are blind. When you are not looking at the interface, for example, you are driving the car, you are talking to some person, you are giving a lecture like this, you are interacting with the objects, and the objects are tangible. You can touch the objects, and when you touch the object, you can easily manipulate it like this. Therefore, it has to, where is it? Therefore, it has to convey physical information along. As you are driving, you are playing with knobs and the buttons in the car without actually trying to understand what they are saying, where they are. You just hold them and rotate them and turn it on, off, whatever, without looking at, because you are doing something else. So therefore, in addition to the people who with disabilities, like the microwave here, with raised letters, which is an add-on, which is a simple add-on. For example, the knobs here, these knobs can be used with much difficulty than this one. So you can understand where this is looking at without looking, but for this one, you have to look. With your hand, you cannot understand. So for example, in the dark, you can't use that kind of knob in the kitchen. We use our touch senses frequently in the daily life without realizing it. Think about no touch feedback in the keyboard. So keyboard feedback in the keyboards are quite important. They are quite important because if you don't feel that your typing got through, you have to see it. And trying to see each letter that you type is very bad. Therefore, screen keyboards on the tablets are not preferred, or keyboards like straight, plain surface is not liked. You have to have some tactile feedback, mechanical feedback on your fingers. For the knobs, for example, you need to have some feedback. You need to realize that you are turning it, it's not broken. So some knobs actually are made stiffer and have some small increments, with very small increments, like when you rotate them, they make noises like trrrt. Therefore, you realize with your hand saying that it is working. So that is what rotational feedback. If you don't get that feedback, you will automatically think that the knob is broken. Knob is coming off from the place. So the mouse button with no click sensor, all other click feedback we sense in the push buttons anywhere are important examples of touch sense in the user interfaces. For example, in the remote control TV, you are pressing the key and nothing is happening. It could be battery dead, it could be keypad not working, TV is far away, or TV is problem, or electricity is out. So how do you understand if the press is not working? The idea is, what they do is they put an LED here. When you press, LED flashes once. That means your press is going through. But again, this button should have mechanical feedback. So as you press, you don't have to look to the LED. You should feel it. But for the technical problems, whether the TV is working or TV is not receiving the issue, some remote control designers put LED here. And some other manufacturers put LED on TV, indicating that when you press the remote control, this one blinks, slightly chirps, so that you realize that your remote control is working. So some kind of feedback is required. Otherwise, if we expect something happen on screen, if it doesn't, how do you know that which one is not working? So the system should be quite strong, fail-proof, for that to be working without cognitive issues. There are two different terms, which is tactile and haptic. When we talk about tactile, that is usually related with our senses on the skin. When we introduce our muscles into the feedback issue, then we call it as haptic. Tactile is very interesting. I have a mouse, and when I touch on the surface of the mouse, it is quite interesting, soft and silky. I say silky. How do I understand something silky? How do I understand that something perfect? Hard. Or I check the fabric of my gear and I evaluate it. I check the quality of the paper. This quality of the paper is something good or something bad, but I can sense it. I can remember things. I can remember a fabric from my childhood, so that if I touch that kind of fabric again, I can say that was the same kind of fabric that I was holding 20 years ago. So there is a kind of tactile memory as well. Think about things that we touch. So we can use that kind of sense for interfacing and information conveying for people with disability or people with regular normal senses. For simulation purposes, we can have haptic devices so that in virtual environments, we can use both. We can have tactile feedback. So you are touching to, for example, a virtual wall, and if we can modulate the surface of the wall, then you can emulate different objects. You can fake person so that the person will believe that he or she is touching to something different. For educational purposes, for interacting with the artificial objects in the virtual environments, haptic feedback is also used. Making haptic feedback is relatively harder because it requires robotics arms that are precisely adjusted. But it can be done, and then you can, for example, simulate a screwdriver operation in a virtual environment. So you can hold the screwdriver and push and rotate. For the tactile senses, these are the keyboards that we are interested. I put a Nokia keyboard there because it was very famous. And there is a click. There is click going on there. So when you press, you can feel that you pressed correctly and you pressed once. If you don't have the feedback, you don't know whether you pressed once or twice or whether you pressed or not. So you have to monitor the screen. So having a good tactile keyboard allows you to stop monitoring the screen, rather focus on the actual task, and your sub-process, your brain, enters the information in a fast and fluent way when the tactile feedback is present with the keyboards, with the regular keyboards as well. In the industrial keyboard, that is quite important. For example, you will enter a dosimeter for the patient in the hospital. 105 enter. For the blood something, injection something. 153 enter. 153 enter. 153. 153 millilitre per hour. If you are hesitant in pressing number 5 may print twice. 153. When you keep your finger a little bit longer on the 5, if the design is incorrect, instead of 153, you will enter 1553, which is 10 times more. 10 times more medicine to the patient, or 10 times more radiation to the patient. That happened. There are well-known stories about that. I have it somewhere else. So in order to prevent those kind of mistakes, for example, key repetition rate must be very long in medical those devices. Otherwise, people may accidentally enter multiple letters of the same kind, because they don't check the value on screen. They believe what they press, and if they hold their finger a little long, that may cause an error. That's because of the feedback. And I'm going to the end. We have a sensory system and we have a motor system. Sensory cortex and motor cortex. It's here. Sensory cortex is somewhere here. Motor cortex is another place. And there are places allocated for the organs. As you see, organs that have high bandwidth, high capacity for information, has more area allocated for the allocated in the brain. One interesting thing in the human, different from the other primates, is area that is reserved for the thumb. Most animals, including chimpanzee, cannot use this thumb with a successful way. So we hold things very successfully. Therefore, the area that is allocated in the brain is much more in humans. Similarly, for the tongue, a lot of space because we talk. For the mouth, nose, but not much for the food. So it's not sensitive here. So not much motor activity happens in those kind of organs. We call this as homunculus model. It was famous in many books. It gives us certain understanding of how we behave, how we act. Also, one important thing is the cerebellum here, beyincik. Cerebellum is an acting buffer between the brain and the motor system, nerves. Brain plans the action, cerebellum creates subcommands for the same action. So if the action requires multiple things, it is done by the cerebellum in addition to the commands from the brain, such as playing piano requires significant amount of cerebellum support because you don't play notes one by one, you play them together. So combination tasks are usually handled by the help of the cerebellum.
Hocam, is motor system of the brain understands better tactile feedback compared to the touch feedback?
Compared to what? Compared to touch feedback, but which one is better?
Tactile versus touch.
Tactile is actually touch. You mean tactile versus haptic?
Oh yeah, touch meaning like in phones and tablets, haptic?
With the phones and tablets, that is also tactile. Huh, without feedback, you mean? Exactly. With the tactile, it is better. With the tactile, it is better, but when you have the phone, you don't have that kind of ability. However, there is research work in having the tactile screen. So they put multiple vibrating motors behind the screen so that when you touch, it vibrates, the whole screen vibrates with very high frequency. You don't feel it. So if your finger is on a button on the screen, if your finger is on one place, it vibrates. If you go to another place, it doesn't. So your finger suddenly starts feeling that part of the screen is raised. Because if you go there, it is up. If you don't go there, it is down. So by the vibration. So as you move through the screen, you will feel that there are raised parts and lowered parts depending on the interface. However, in reality, it is all glass. That is done.
So why are some car companies, get away with using touch everywhere instead of tactile buttons? If it is worse than touch.
That happened in the year 2002. Electronic dashes were very popular. Then they realized that it is not usable at all. These displays are quite cheap. Having mechanical interfaces are very expensive to build and install. For the installation is also requires manpower. But combining everything into one big screen and having touch controls are easy and cheap. That is only for the cost reasons. Also, they advertise it for a fashion.
Technological.
For a fashion. So people like it if they have big screen like Tesla. But actually, in order to use those kind of interfaces, you need to look at it. My old car, I bought it in the year 2000, has electronic climate control. Recent one has also electronic climate control, but the one I have in the year 2000 has up and down buttons. Mechanical buttons, but up and down buttons. And in the display, you have 26 degrees, left and right, whatever. In order to change it, also another up and down on the right. In order to change, you have to push to up and see what the number is. So you have to look at it. But the recent one has rotating knob. So if I want to increase it, I just hold it and rotate a little bit. So if I know that if I rotate little bit, the changes will be little bit. In this one, I have to monitor the number on the screen by eye. So obviously, the later design has a rotating knob and display on it. So you rotate it, and after you rotate, you glance to the display and see what the temperature is. But the recent cost-cutting cars totally eliminate those, and they let you do everything through the touch panel, including temperature control. Because most people don't change it. I don't change it either that much. It's all the same. Yeah. Tactile feedback is good. In the cars, especially, they may switch to voice interfaces, because voice interface, if it is successful, voice interface also will be cheap, because you can eliminate display, and that's a huge cost. Let's do the last thing here. We have the Fitts law. The Paul Fitts in 1954. In 1954, they made this experiment, in experimental psychology, with the stylus and with the distance and with the size of the target. So they asked people to hit left and right as fast as possible without making an error. There is a metal plate here that will ring. If they make an error, that's false. If they make the correct hit, that's positive. So they can count positive and negative hits with electrical signals, this cable going on. So they can measure how fast a person can select items without errors or with a given error. They realized that there is a logarithmic relation which is very significant, and basically, as the target becomes more distant, time increases, and if the width of that's D actually, that's W, width for the width of the target and distance for the target distance in between. As the width increases, performance is better. You can hit faster for the bigger targets, and for the distant targets, obviously, it takes lower. But the ratio was logarithmic, and the Fitts law was saying that the time it takes as some certain constant, that is what reaction time is, plus a coefficient on logarithmic scale, distance over size. So if the size is bigger, time is shorter. If the distance is bigger, time is longer, but with the logarithmic scale. So it has more effect when they are small. It has less effect when they are big. And yeah, and actually this reaction time is also dependent on size of the target. If the size of the target is too tiny, then you have more preparation before starting to move. Normally, you are here, your target is here, at the beginning you are here, you move and click. If the target is very small, preparation time is longer because more cognitive load is present. What this tells us? The menu sizes, button sizes. If you make the buttons too big, then distance becomes issue. If you make them small, then size becomes an issue. So it will be something in the middle so that they will be clicked with relatively easy manner. Also, frequently used items should be placed on top of the menu, because at the beginning you are at the top of the menu and you will pull down the menu. If it's pull down menu, the road you should travel becomes longer for the elements at the bottom. So frequently used items should be put at the top so that it takes less amount of time and less errors are done. So for today, we have finished the input and output channels, and the characteristics of these input and output channels determine the nature of interaction. And for each information channel, we need to consider the capacity, reaction time, usage method, fatigue, interface, interference between different channels, and more importantly, capacity of the channel. Capacity of the visual channel is a lot. However, there are different issues. For example, sound channel has the minimum reaction time. So if you want to warn somebody, sound is the fastest one. Then visual, then touch, then burn. So, for example, you touch to the stove, you burn before you feel it, because burning sense is quite slow. So that cannot be used for, therefore, heat interface cannot be used for conveying information. But touch is fine. But if you are going to warn somebody as early as possible, in a very fast way, you want to reduce the response time, then use sound together with the other channels. Yeah, today I think it is sufficient for today. Next week, I'm going to continue to the memory issues and learning. And if you have any questions, let me know. I am stopping the recording.